our techniques for polynomial division and dive deeper into the remainder theorem and the factor theorem. The remainder theorem says that if we substitute a number into our polynomial using synthetic division or any kind of division, if there is no remainder, then we know that it is a factor. However, if there is a remainder, we know that it is not a factor. So if I'm given f of x is equal to 2x to the 5th minus 3x to the 4th plus x cubed minus 2x squared plus 8x minus 8, we want to find the value, our function value of f of 10. Now remember that if I have f of 10, this is really saying that my x value is equal to 10. So when I substitute this in utilizing our synthetic division of 10 here, we all know we bring down the 2. Synthetic division says that we write the coefficients along the top. And I notice that I have 5, 4, 3, 2, 1, and no powers of x. So when I bring down the power, the value of 2, 2 times 10 is 20. Negative 3 plus 20 is 17. 17 times 10 is 170. Plus 1 is 171. Times 10 is 1,710. When I subtract 2 from that, we have 1,708. We're just getting larger and larger here, providing me with 17,081. And 170,810 minus 8 still gives me 170,802. So when we plugged in the value of f of 10, we have 170,802. That tells me that the value of x minus 10, since if I were to have x equals 10, if I were to put this back, minus 10, I would have x minus 10 is equal to 0. Working backwards. This tells me that the factor x minus 10 is not a solution since we have a remainder. Let's determine whether 5 is a 0 of our g of x function, which is x to the 4th minus 26x squared plus 25. So if 5 is a 0 of our function, then when we plug in g of 5, our y value would have to be 0. Because again, we're looking for where our graph is crossing the x-axis. And x minus 5, and we would be a factor, and we would have a remainder of 0. Therefore, 5 would be a 0 of the function. We're going to use synthetic division. So we're going to try 5. Notice when I have my value here, I'm missing the x cubed. So I'm putting in a 0 for the x cubed place. I'm also missing a regular x, so I put a 0 in for regular x. We bring down the 1, so we have 1 times 5 is 5. 0 plus 5 is 5. 5 times 5 is 25. Negative 26 plus 25 is negative 1. 5 times negative 1 is negative 5. 0 plus negative 5 is negative 5. And 5 times negative 5 is negative 25, so we have a remainder of 0. Since when I plugged in my value of 5, we ended up with 0. This tells me that 5 is a 0. So my function x minus 5, my binomial, is a factor. And this piece here will give me my reduced polynomial. So those are my coefficients of my, let's see here, no x's, x to the first, x squared, x cubed. So my reduced polynomial now will be x cubed plus 5x squared minus x minus 5. If I were to multiply and distribute these through, I'd end up back where we started with the x to the 4th. Determine whether the imaginary value of I is a 0 of the function x cubed minus 3x squared plus x minus 3. It's written in descending order. I don't have any missing pieces. So we want to know if I is in a solution. So we'll start off by putting I in our box here. We will bring down our 1. 1 times I is I. I can't actually combine like terms here. So I'll have -3 plus I. But now I need to take I times -3 plus I. So I'm going to do a little side work. This gives me then -3I plus I squared. We know we replace I squared with -1. So this provides me with -3I minus 1, or -1 minus 3I. When I add 1, combining like terms, those disappear, so I only have -3I left. And -3I times I gives me -3I squared. Again, replacing I squared with -1. This gives me a +3. So we end up with 0. So since f of I is 0, we know that I is a 0 of the function. Let's determine whether I is a 0 of the function f of x is -2x cubed plus 8x squared plus 5x minus 1. Again, I'm going to put I on the outside and use the coefficients on the inside. I have cubed, squared, first power, no power. So I have all of my pieces in descending order. I'm not missing any values. All right, I'll bring down -2. -2 times I is -2I. I'll then have 8 minus 2I. I'm going to do a little side work here. I need to take I times 8 minus 2I, which is 8I minus 2I squared. Replacing that I squared with -1 provides us with 8I plus 2. So I'll bring 8I plus 2. Combining like terms, I'll still have 8I plus 7. Again, I need to take I times 8I plus 7. Distributing, I have 8I squared plus 7I, or -8 plus 7I, so -8 plus 7I. We now have -9 plus 7I as our remainder. So we have a remainder. So since when I plug in I, we ended up with -9 plus 7I, so we know that I is not a 0 of this function. So there's not an invisible 1 that's there. The factor theorem says that for a polynomial function, if there is a value and we end up with a remainder of 0 when we plug it in, we know then that it is a factor of that function, just as we talked about. So back at that example 1 here. So since we example 2, since we ended up with a 0 here, I then know that x minus that value is a factor of the function itself. So let's let x be x cubed minus 3x squared minus 6x plus 8 and solve the equation. So according to the factor theorem, if we plug in a value and we end up with 0, then x minus c is a factor. At this point, all we have are the skills to make some arbitrary choices. We're just going to try some possibilities to determine if they actually are. In upcoming lessons, we'll have a better idea of what we can choose and kind of narrow our choices down. But for now, all we have are to go on is to just make guesses until we get there. So let's try -1 as an example. So let's first try -1. If we find out that -1 is a factor, then we know that x plus 1 will be the factor itself. And our original function is f of x is x cubed minus 3x squared minus 6x plus 8. So let's try negative 1. I bring down 1. Negative 1 times 1 is negative 1, adds to negative 4. Negative 1 times negative 4 is positive 4, adds to negative 2, which provides us with a positive 2 and a 10. Since 10 does not equal 0, we know that negative 1 is not a 0 and it does not cross the x-axis at negative 1. Therefore, our factor of x plus 1 is not a factor of our function. So negative 1 doesn't work. Maybe we should try positive 1. So let's start over and try positive 1. Bring down my 1. 1 times 1 is 1. That still will give me negative 2. 1 times negative 2 is negative 2. Adding together is negative 8. 1 times negative 8 is negative 8. Aha, we found 1. We found 1. So I know that x minus 1 is a factor because right now I say that it crosses the x-axis at 1. So if I want to put this back in its factored form, we would subtract 1 from both sides. So x minus 1 equals 0 is the factor itself. And again, here we have the reduced polynomial. Right now I have x minus 1 times, again, no x's, x squared. The coefficients would be 1x squared minus 2x minus 8. Again, this piece here is what we call the reduced polynomial. And we have found a current factor. But it's not all the way reduced down. It's not all the way factored. But now I have it in an x squared form. And since I have it in x squared form, I can continue factoring by using our regular factoring techniques, such as factor by grouping. Perhaps we could factor by using the table. You could use the quadratic formula. You could complete the square. Any of those possibilities for solving a quadratic we can use here. Since there's nothing in front of x squared, I'm going to find two values which multiply to negative 8, but yet which add to negative 2. It looks like negative 4 times 2 will get us there. So I can factor the x squared minus 2x minus 8 into x minus 4, x plus 2 with that x minus 1 at the top, on the left. Now that it's factored, we can find and finish solving because we can set each factored piece equal to 0. X minus 1 is 0, x minus 4 is 0, and x plus 2 is 0. Therefore, our solutions are x is 1, x is 4, and x is negative 2. It shouldn't surprise us that we found 3 solutions since our exponent in the beginning function was x cubed. So it shouldn't surprise us that we're looking for 3 of them. So let's look at x cubed plus 2x squared minus 5x minus 6, and let's factor and solve the equation. So I'm just going to start off just with a random number. I would start out with values that are close to 0 and work your way out, both the negative and the positive, keeping in mind that we're only going to be working with whole number solutions right now, and we'll talk about how we can find the rest after a while, in upcoming lessons, I should say. So let's start with negative 1 and see if we can't reduce this polynomial down. I have x cubed 2x squared minus 5x minus 6, so I have all the pieces in my polynomial. The most amount of factors I should have are 3 real ones. There could be imaginary ones in upcoming lessons, so keep that in mind. My coefficients are 1, 2, negative 5, and negative 6. So I bring down 1. Negative 1 times 1 is negative 1. 2 times negative 1 is 1. Negative 1 times 1, negative 1. Negative 6, positive 6, and 0. Oh, great. We found a coefficient we found a 0 right away. Therefore, x plus 1 is a coefficient right away. Because right now I say x is equal to negative 1, I need to add 1 to both sides. So x plus 1 equals 0 is our current factor. Our reduced polynomial then is going to be 1x squared plus 1x minus 6. And we want to continue to solve this. Now that I have this piece in an x squared, I'm going to want to factor these by finding two numbers which multiply to -6 but yet add to -1. 3 times -2 works. So its factored form will be x plus 1, x plus 3, and x minus 2 equals 0, setting them each equal to 0. I now have my solutions of x is -1, which we found here, and by factoring I found the other two solutions. And you can always check by graphing. So if we were to graph this polynomial, we would see that our graph would cross the x-axis at -1, -3, and 2. And this concludes our lesson on using the remainder theorem and the factor theorem in order to help find the solution of polynomials.